One more theory we'll discuss, that is the distortion energy theory for ductile material. Now this theory is based on the distortion energy. Consider here a hydrostatic stress system and we have three stresses are acting sigma in all the three directions. So when the ductile material are subjected to hydrostatic stress, that is a even kind of stress on each face, basically all the same, and hence the yield at much higher yield strength than subjected to non-hydrostatic stress, because the inner layers here are essentially stress that part or compresses or stretch it. So yielding phenomena is not just a simple tensile or compressive phenomena, it is more probably the angular distortion. So ductile materials are straight hydrostatically exhibited the yield strength greater in excess of the value given by the simple tension test. Therefore, it was postulated that yielding was not a simple tensile or compressive phenomena at all, but rather that it was related to somehow to the angular distortion of the stress element. So here objective is to find out the value of the shear or the distortion strain energy. And once we are able to calculate the shear or the distortion strain energy, then we can use the distortion energy theory for the ductile material. So according to the definition of distortion strain energy theory for a ductile material, the failure will occur when the distortion strain energy in the material exceeds the distortion strain energy in a tensile test specimen. So you have to first calculate here what is the distortion energy in the material, and then you have to calculate the distortion energy in a tensile test specimen. And the value of the distortion strain energy in a tensile test specimen is always higher value than the distortion strain energy in the material, then the material will not fail. Otherwise, the material will fail. So this criteria is used in defining the distortion strain energy. So consider here a cube which is subjected to three-dimensional stress test as designated as sigma 1, sigma 2, sigma 3. So sigma 1, sigma 2, sigma 3 are the three principal stresses. So because of sigma 1, sigma 2, sigma 3, this element will undergo both the volume change as well as angular distortion. So because of sigma 1, sigma 2, sigma 3, three principal stresses on the cube, the element will undergo both volume and the angular distortion. So we'll split up these three principal stresses into two figures. One will consist of the element undergoing the hydrostatic tension, which has only the volume change, and the second element has an angular distortion without volume change. So let's show this figure is consist of two more figure. One is the hydrostatic tension and second is the angular distortion. So hydrostatic stress, you have to take the average of sigma 1, sigma 2, sigma 3. So we have sigma 1 plus sigma 2 plus sigma 3 divided by 3, which one is represented as a sigma average. So this one is also sigma average. So if all the stresses are equally in magnitude, then it represents a hydrostatic stress condition. And this value of sigma average is same as 1 by 3 of sigma 1 plus sigma 2 plus sigma 3. Due to the hydrostatic tension, this element will undergo only the volume change. So because of the three principal stresses, sigma 1, sigma 2, sigma 3, will have element undergo both volume and the angular distortion. One part we'll consider here as a volume change due to the hydrostatic stress. Then the other part we'll consider here is due to sigma 1 minus sigma average, sigma 2 minus sigma average, sigma 3 minus sigma average. That will give you the angular distortion without volume change. So if we write the stresses as sigma 1, and already we have introduced here sigma average, so this stress will be sigma 1 minus sigma average. This stress will be sigma 2, and we have used the sigma average is minus of sigma average minus sigma average. So this element undergoes the angular distortion without volume change. So this idea was used to calculate the shear or the distortion strain energy for any element which is subjected to stress sigma 1, sigma 2, sigma 3. We have to divide this stress element into two parts. One is subjected to average stress and other part is the difference between sigma 1 and sigma average, sigma 2 and sigma average, and sigma 3 sigma average. Due to the three stresses sigma 1, sigma 2, sigma 3, we observe that there undergoes a volume and the angular distortion. So one part will consider purely the volume change and no angular distortion. Because of the second part will consider the angular distortion without any volume change. Now as far as the strain energy considered with the sigma 1, sigma 2, sigma 3 is given by the equation 1 upon 2 times of E sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 times of Poisson ratio multiplied by sigma 1 into sigma 2 plus sigma 2 into sigma 3 plus sigma 3 into sigma 1. And if we have all the stresses are equal in magnitude, then we can calculate the strain energy of a three-dimensional hydrostatic stress system as 3 times of average stress square divided by 2 times of Young modulus multiplied by 1 minus 2 times of mu. So we know the strain energy per unit volume of generalize the stress element, and we know the strain energy in the case of hydrostatic, so we can very well calculate the strain energy for the distortion model. So this value of strain energy is same as the total strain energy minus the strain energy in case of hydrostatics. So let's say U represents here the total strain energy if the element undergoes a stress sigma 1, sigma 2, sigma 3. This value of U is same as equal to the strain energy due to hydrostatic stress equal to sigma H plus we have the strain energy due to distortion, which is represented by UD, and we are interested to calculate the value of UD. So in this case the strain energy due to distortion UD is same as equal to total strain energy U minus the strain energy due to hydrostatic stress, and we'll substitute for U as this equation and UH as this equation. So we have total strain energy due to the three principal stresses sigma 1, sigma 2, sigma 3 is given as 1 upon 2 times of E into sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 times of mu, that is the Poisson ratio, into sigma 1 sigma 2 plus sigma 2 into sigma 3 plus sigma 3 into sigma 1. Next we have to calculate the value of UH, that is the strain energy due to hydrostatic stress. And the strain energy due to hydrostatic stress we have calculated as 3 times of sigma average square into 1 minus 2 times of mu divided by 2 times of E. Here sigma average will be equal to sigma 1 plus sigma 2 plus sigma 3 by 3. So you have to make a square of it and you have to expand this term. So let's substitute here the value of sigma average equal to sigma 1 plus sigma 2 plus sigma 3 by 3. We'll make a square and we'll expand it. So let's expand here the expression for the strain energy for hydrostatic stress by replacing sigma average equal to sigma 1 plus sigma 2 plus sigma 3 by 3 whole square. So we have UH equal to 3 divided by 2 times of Young modulus multiplied by, you have to make a square of this term. So square of this term will be same as equal to sigma 1 square plus we have sigma 2 square plus we have sigma 3 square plus we have 2 times of sigma 1 into sigma 2 plus we have 2 times of sigma 2 into sigma 3 plus we have 2 times of sigma 3 into sigma 1. This 3 is in the denominator, so you have to make a square of this term also, divided by 3 square and again multiplied by one term is left here, that is equal to 1 minus 2 times of mu. So in denominator we have 3 square, in numerator we have 3, so one of the 3 will be get cancelled. So this 3 and 1 3 will get cancelled. 3 into 2 is 6. So we left here with 1 minus 2 times of Poisson ratio, that is this term we are writing, divided by 2 into 3 is 6 multiplied by E and again multiplied by sigma 1 square plus sigma 2 square plus sigma 3 square plus we have 2 times of sigma 1 into sigma 2 plus we have 2 times sigma 2 into sigma 3 plus we have 2 times of sigma 3 into sigma 1. So this one is the final expression for strain energy in the case of hydrostatic stress. So this one is our expression for the strain energy in the case of distortion. This one is the expression for strain energy due to three principal stresses, sigma 1, sigma 2, sigma 3, and this one is our expression for strain energy due to hydrostatic stress. So we'll put here 2 and 3 back into 1 and we'll solve for the strain energy due to distortion. Now that substitution will take a long time here, so I will give the final equation for the strain energy due to distortion. So finally we left here with strain energy due to distortion equal to 1 plus Poisson ratio mu divided by 3 times of E is multiplied by sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square, and whole thing is divided by, since I written here 3, I have to divide by 2. So 3 into 2 will be same as equal to 6. So finally we are left here with distortion strain energy is given as 1 plus mu divided by 3 times of E into sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square divided by 2. This value is for any case. Whatever the type of loading we have, we always get the distortion energy per unit volume as given by this equation. So first part we have done, that is distortion energy in the material we have find out. Next we have to calculate distortion energy in a tensile test specimen. So when we carry out the tensile test, then we have only stress present is value of sigma x. At yield point, this value will take equal to SYT, and this one is the maximum principal stress that equal to sigma 1. Other two value is sigma y is 0 and tau xy is 0. So we have sigma 2 will be equal to 0, as well as we have sigma 3 is also equal to 0. So this expression for distortion strain energy we can use now. We can substitute for sigma 1 equal to SYT, sigma 2 and sigma 3 equal to 0. So we get here the maximum distortion strain energy according to the test specimen is equal to, we have 1 plus mu as it is divided by 3 times of E, and inside the bracket we have sigma 1 whole square, this value is 0. Sigma 1 whole square is same as SYT square. Second term will be equal to 0. And this one is the square of sigma 1. So that will be again equal to SYT whole square and divided by 2. So in numerator we have SYT square plus SYT square is 2 SYT square. 2 and 2 will get cancelled. And the final expression for maximum distortion energy for test specimen will be equal to 1 plus mu divided by 3 times of Young modulus multiplied by SYT whole square. So according to the distortion energy theory, the failure will occur when the distortion energy in the material, that is value of UD, if exceed than the value of distortion energy in a tensile test specimen. So this value if exceed than UD maximum, then we have a failure. So I just plug in this value of UD from this equation, which is 1 plus mu divided by 3 times of E into sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square divided by 2 must be greater than 1 plus mu divided by 3 times of E into SYT square. So this term is common in both sides, so that will be get cancelled. So finally we left here with sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square divided by 2, and we have SYT square. If you take a under root here, then you get expression for the von Mises stress. So left hand side under root will represent as the von Mises stress. So we have sigma prime, which one is representing the von Mises stress, is same as equal to sigma 1 minus sigma 2 whole square plus we have sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square, and whole thing is divided by 2, and you take the under root of this, so power is 1 by 2. If exceed than SYT, then we have a failure. So remember the definition of the von Mises stress, which is sigma prime, is under root of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square divided by 2. And if this value of the von Mises stress is less than equal to SYT, then the material is safe. So in this case, we can calculate the factor of safety N. So we have factor of safety N will be same as equal to SYT divided by the von Mises stress, which is given by this equation, the factor of safety for distortion energy. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.